Let us discuss some of the important terms associated with coordination chemistry. First of all, we should know what is coordination entity, that is entity. Coordination entity. This constitutes a central metal atom with surrounding ions or molecules. Example: CO, Cl3, NH3 3 times. So here CO is the cobalt is the central metal atom, and the surrounding ions are chloride ions. There are 3 Cl minus ions. Molecules, that is neutral molecules, surrounding neutral molecules, and this is the central atom, metal atom. Surrounding neutral molecules is, here the molecules are ammonia, so there are 3 ammonia molecules. And in fact, these surrounding molecules or ions are called ligands. And the number of ligands is called coordination number. Coordination number. Now, what is the coordination number of cobalt in this complex compound, that is coordination compound? There are 3 chlorine and 3 ammonia. So you can say the coordination number of this complex is 6. You understand? In fact, these ligands are bound with the cobalt with coordinate bond. Next one. Let us talk about the central atom, central metal atom. It can be an atom or ion, usually metal, usually transition metal. Let us consider nickel, Cl2, 4 moles of water. And we can actually work out the oxidation state for this. Here For water it is 0, for chlorine it is -1. And the net oxidation state of this neutral complex, this is a neutral complex, because a complex ion can be formed as cation or anion. Sometimes it is available as neutral compound also. So in this case the oxidation state of this complex is 0. Therefore you can put X for this. So X plus 2 of -1 plus 4 of 0, 0 is equal to 0. Therefore X is equal to plus 2. See the oxidation number of nickel in nickel chloride Cl2H2O 4 times complex is plus 2, and it should be indicated as Roman letter, that is 2. When we coin the name, when we call by IUPAC name, it should be associated with the central metal atom as nickel 2. Now these central metal atoms are also referred to acids, Lewis acids. Why they are called Lewis acids? Lewis acid means that is an electron, for example, when it is accepted, it is called acid. Let me explain based on ammonia. We have got ammonia NH3, and you got a lone pair of electrons. When HCl is combined, this proton is already given electron to chlorine for formation of HCl. So it needs another set of electron, and actually that is donated here. So this acts as the donor. Okay, which one? Ammonia. So N, H, H, and a bond is donated, so H, and then Cl minus. So since it has donated a pair of electrons here for the formation of coordination bond, and it has lost one electron, we can put NH4 plus, and that's why ammonia becomes ammonium. When it is available as cation, this IUM suffix is added, so ammonium chloride we call it. So this is a very good example for Lewis base. This Lewis base, why ammonia is called Lewis base? A pair of electron is donated, and hydrochloric acid, it accepts the pair of electrons, is it not? So that is why they are called Lewis acid. Now in the case of complex from the ligands which are enriched with electrons, and they will be having so many pairs of electrons, they will be donating their electrons to the central metal atom, and thereby it acts as acid because electron acceptor. So it's also called Lewis acid. Take down, which is called Lewis acid. Central metal atom also called Lewis acid. Why? Because they are electron acceptors, actually electron pair acceptors, electron pair acceptors. Are you able to follow? And thereby it forms, for example, you have got the metal, the ligand is donating an electron, so he is the donor, ligand is the donor, and here metal is the acceptor. Are you able to follow? And that is why it's called Lewis acid, and this one is Lewis base because it donates electron. Do you understand? Next. Now let us talk about the ligands. Ligands are classified based on the number of attachments as monodentate ligand, dent means tooth, so monodentate, it can have a point of attachment at one place. Bidentate ligand at two place. Tridentate ligand at three place. Likewise, polydentate ligand. So this is either mono or you can call it unidentate ligand. Unidentate ligand. And when they have many number of points of attachments, like in the case of EDTA, ethylene diamine tetraacetic acid, it has 6 points of attachment, so that is why it's called hexadentate. 6 points of attachment. With central metal atom. These ligands can be simple ions like chloride, bromide, iodide, sometimes small molecules like water, ammonia, neutral molecules, and sometimes larger molecules, sometimes it can have much bigger, that is macromolecules. Like in the case of proteins. Usually these ligands are surrounding the central metal atom. You have got the metal atom here. There will be a ligand, 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 like this. L represents ligand. And it can have like this also. And based on the number of ligands, the coordination number is given. If there are 6 ligands, the coordination number of the complex is 6. If there are 4, you can call it 4 is the coordination number. Now, bidentate ligand, we can discuss about this ethylene diamine. Polydentate ligand, this is EDTA. And you got another example like oxalate. We will explain all these things one by one. Now, this is ethene. and the common name is ethylene. IUPAC is ethene. CH2 single bond CH2, and here you have NH2 NH2. This is called ethylene diamine. This is one amine, another amine, and this is ethylene. So commercially or commonly it is called ethylene diamine, single M. Okay, and by IUPAC nomenclature 1, 2, that is ethane. Okay, and you got amine group on one side and another side another amine. So ethane 1, 2 diamine. Ethane, this is IUPAC. IUPAC is ethane 1, 2 diamine, single M. Okay, ethylene diamine, and it can have 2 points of attachment. Why? Because a lone pair of electron is available here, another lone pair of electron is available here. So it can have 2 points of attachment. For example, CH2 and NH2 NH2. So you got the pair of electrons here. Okay, so this will attack at 2 places. Okay, so this is a bidentate or didentate ligand. Bidentate or didentate ligand. Because the points of attachment is 2. The point of attachment is 2. Next, let us talk about oxalic acid. This is carboxylic acid group. Carboxylic acid group, and COOH. This is monocarboxylic acid because it has got one COOH. When there are 2 COOH, it's called dicarboxylic acid. And also called oxalic acid. And you got 2 carbon. 2 carbons means eth. So it is basically rooted from ethane. So it's called ethane dioic acid. Okay, so it can be called by IUPAC 1,2-ethane dioic acid, or simply it can also be called oxalate anion. Actually this oxalate, this is oxalic acid and this is 1,2-ethane dioic acid. That is oxalic acid. And oxalate is COO minus COO minus. This is oxalate. Okay, and this can be represented as H2C2O4 as oxalic acid, and this can be represented as ion, that is C2O4 2 minus. So oxalate anion. So this can be represented by C double bond O C double bond O, and you have O minus, okay, take down. You have to do all these things. So this is the bidentate ligand, oxalate. Similarly, you have EDTA. EDTA, take down, ethylene diamine single M tetra acetic acid. Ethylene, let us develop the structure one by one. Ethylene, CH2 double bond CH2. Ethylene diamine, so CH2 single bond CH2, you have one NH2, another NH2 here, okay, and ethylene diamine tetraacetic acid. So here NHH, CH2, CH2, you can put N with. Now you have CH3COOH, and that is attached here. So CH2 COOH, instead of H you can put minus. So let us put here H, and then in the second stage we will put minus. This is called tetraacetic acid. COOH. Okay, so this is known as EDTA. And this EDTA as salt. So CH2 single bond CH2 and H, is it not? NH we have. So CH2 COO minus, CH2 COO minus, CH2 COO minus. Now, where are the place they can have the point of attachment? I said it will have 6. Now you have one set here, another set here, 2, and on each oxygen another set. Okay, so totally how many? 1 2 3 1 2 3 6. So the 6 points of attachment, like in the case of octopus, it can handle the prey with all 8 tentacles. Likewise, this is like hexopus, we can call it. Okay, it will have 6 holding. It will have 6 arms, and with these tentacles, it will hold the central metal atom. Okay, take down. So this is EDTA. So this is hexadentate ligand. Such type of ligands, okay, with the polydentate type, they usually form that is a ring based coordination compounds. Okay, that is called chelation. Take down. Such bidentate or polydentate ligands form chelation chelate carbonate, chelate complex compound. So they are called chelate ligands because chelation means forming ring structure with central metal atom. Okay. So what is the denticity of EDTA? The denticity means denticity of EDTA is 6. It indicates 6 points of attachment with the central metal. I've taken down, and then coordination sphere. Coordination sphere. For example, K4 Fe Cn 6 times. So this portion is called coordination sphere. Okay. So normally it is enclosed by square bracket. And outside this bracket are ionizable. If any compound is present, for example, K4 is outside the coordination sphere. Okay. Therefore, K4 Fe Cn 6 times means when it is ionized, it forms a 4K plus, and this results Fe Cn 6 times 4 minus as complex ion or complex anion. Okay, please make a note of it. Next one. Coordination polyhedron. Coordination polyhedron. The spatial arrangement of ligand atoms, it is directly attached to the central metal atom. That defines the coordination polyhedron. For example, this polyhedron can be of various types like octahedral, tetrahedral, square planar, trigonal bipyramidal, and square pyramidal. See, the structure will be like this. Let us consider the metal atom at the center. So you will have the central metal atom like this, L, 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 and upward, downward, L. Why it's called square planar? Because it is bound like this. This is the square planar bipyramidal. So you have one square and over which one pyramid, another at the bottom, next pyramid. So square planar bipyramidal is also called octahedral because it has got 8 edges. For example, from the top 1, 2, 3, 4 and 1, 2, 3, 4. So 4 plus 4, 8. Similarly, you have tetrahedral arrangement also. Tetrahedral will be like this. We have the central metal and one, two, three, four. L, 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 L. And square planar will be M at the center. That's all. Legon, 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 Legon. You can have a link like this to understand the shape. And here, like this. Okay. Trigonal bipyramidal. So you got the central metal here. Legon, Legon, Legon. Trigonal bipyramidal. Legon, another Legon. Okay. So this is actually, this is trigonal and bipyramidal like this. Okay. And square pyramidal. So on one side only. That is Legon, central metal atom, Legon, 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 on the top another Legon. Okay, this is called square pyramidal, whereas this one is on both sides, top and bottom. So square planar bipyramidal. This is square planar pyramidal. That's all. Whereas M represent central metal atom, L represent Legon. And finally, we need to discuss about homoleptic and heteroleptic complexes. Homoleptic and heteroleptic complexes. When a central metal atom is bound to one kind of donor group, that is one kind of Legon. For example, CO, NH3, 6 times 3 plus. Okay, this is a complex cation. Okay, complex cation. So you have one type of Legon around the central atom, central metal atom. So that is why it's called homo. Homo means single, homoleptic complex. In this case, that is CONH3 4 times Cl2. So here you have two different types of ligands. Okay, so it is called, this is one ligand, this is another ligand. So two different ligands, different types of ligands, and that's why it's called heteroleptic complexes. Okay.